So I'm going to talk about three main things. So firstly, are invertebrate communities actually affected by microclimate change? Secondly, are we measuring microclimate variables at appropriate scales? And then thirdly, a sort of conceptual idea for how we might move beyond our kind of traditional methods and stuff for the future. So we all know that the forest in Borneo is being logged and turned into oil palm. And this affects ecosystem processes and biodiversity in lots of ways. The one thing it changes immediately and quite profoundly is the microclimate. So primary forests are quite kind of cool and homogeneous, and then logged forests are a bit hotter than that, and plantations are quite considerably hotter. And this is important for lots of things, but invertebrates, as we've seen from some of the other talks so far, are really important in mediating functions. And they're also very small and they're ectotherms, so they're quite sensitive to their conditions surrounding them. So firstly, also, we always assumed that insects would be affected by microclimate change, but when you go through the literature, everybody kind of invokes that as something in their conclusion, and there's not really actually any data which measures it specifically. So firstly, we went out to measure if microclimate affects insects, and for that you need to measure three things. So we measured the thermal tolerance of a bunch of ants. We used the existing microclimate data that Stephen Hardwick collected, and then an ant community data set that Sarah Luke had collected. And we collected data for this many ants and used the extensive microclimate. And then that was the size of our ant community. So comparing the thermal tolerance of species versus their microclimate, and then the changes in relative abundance between habitats that differ in their microclimate, you can see whether those communities that are existing there are defined by a relationship between microclimate and physiology. And what we found was this. So as CT max increased, the relative abundance in the different habitats moved from kind of mostly living in the forest down here to being much more abundant in oil palm up here. And the changes between these habitats were all significant as well. So each one of these is moving from a cooler to a warmer habitat with change in relative abundance on the y-axis and thermal tolerance on the x-axis. So as thermal tolerance increases, moving from a cool to a warm environment, your relative abundance increases as well. So that was all great. We'd found out that we'd identified this knowledge gap and showed that invertebrates were being affected by microclimate. But when you look at the scale of this x-axis, so 40 to 47 degrees, that's the physiology of the ant community, it's safe. But then at the microclimate data, so we're looking at kind of 25 degrees, 26 degrees, and up to about 31.5 degrees. That's much, much lower than any of the upper physical tolerances of even the bottom level of the ant physiology. So we wondered, are we measuring microclimate at a scale that's relevant to the ant community? So I went out to test that next. So the body temperature of an ant is not only defined by convection, which is its surrounding air temperature, but by conduction from objects, radiation from the sun and reflectance of surfaces, and also metabolic heat production. And ants are incredibly small, so they exist in thermal boundary layers that exist just a few millimeters above forest substrates. And they've been shown to be able to be heated to much hotter than surrounding air. So it's likely that these two microclimate factors are more important for small-bodied ectotherms than ambient air temperature. So how did we test that? We went out into the forest and we made a 20 by 20 meter grid where we collected lots of hemispherical images so we could know what the canopy structure was and how much sunlight was being filtered down to the forest floor, which would obviously affect the temperature of forest surfaces. And then beneath that, we made a 5 by 5 meter grid where we collected 100 thermal images And above each image, we also collected the ambient air temperature, so we could use that as a kind of paired comparison. And when you stitch all those images together, you get these kind of representations of 5 by 5 meters of the forest floor. So we got 51 of those across the landscape, and each one contains about 4 million data points of temperature recordings. So when we compared surface and ambient temperatures, we found that we were underestimating the magnitude of microclimate change across the land use gradient by only looking at air temperature, or that's relevant to these small ectotherms. So for mean temperature here in graph A, surfaces were cooler generally than ambient temperatures in good quality forests up to 90% canopy cover. And that gradient of that line is much steeper, and it's much, much warmer than air temperature in the less quality forest. So these red squares here, red pluses, sorry, are relevant to these example thermal images down here, just as a kind of to show you roughly what they look like. And then maximum temperature increased much, much faster in surfaces than ambient temperature. And so if these are probably a stronger like filtering effect when we're looking at physiology, because they get closer to the absolute physical threshold of a species, and we're underestimating those by over 10 degrees in the most disturbed habitat types. So we wanted to know how this was directly relevant to the functioning of organisms. So I generated these curves for the foraging efficiency of two of the most common genera of ants, so Pheidole and Chromatic aster, which are found all throughout the forest at SAFE. And by referencing for every 0.1 temperature increase, every 0.1 increase in foraging efficiency across this curve, and then replacing the temperature values in the original images with the foraging rates, you get this really nice picture of how this genera, which is mostly associated with really good quality forest, you can see how its niche space is being eroded as canopy cover decreases, and the opposite becoming true for this one. But even in the most disturbed forest types, this one starts to lose habitat as well because it's being pushed. The temperatures are going really extremely high. And you can see that here, just a regression showing that effect of canopy cover increasing and the fitness for this one increasing and for this one decreasing. And also when compared with, if you make the same metric from ambient temperature, we're getting inaccurate predictions of the functional rates of these important organisms by only looking at air temperature. So what that kind of tells us is, yes, ambient temperatures underpredict the magnitude of microclimate change. And this means we might actually be overestimating the capacity of logged forests to function and harbour biodiversity in the face of climate change. And generating accurate predictions of responses to temperature change are really vital if we want to understand how those forests will persist in the future. And this also got me thinking about this point, which is traditionally in kind of ecophysiology, we've looked at the physiology of organisms, so their respiration or growth, and how that relates to temperature, and then assumed from that what the functions that they mediate in the forest, how would they be affected by temperature changes. But actually generating performance curves for the functions themselves rather than for the organism, and then replacing the values in those maps like I showed before, that's actually a much more ecologically important way of looking at temperature change. So that leads me on to this third point, which is just a sort of conceptual idea, and it's something that I'm getting at in the third final chapter of my PhD, which is using those notions of traditional physiology and applying them to functional processes rather than to organisms, and how we can then get a better idea of landscape scale effects of climate change and deforestation, rather than inferring from our knowledge of how it's affecting species. So that, just to kind of use this as an example, normally people have used like these extreme values of their like thermal minimum, thermal maximum or optimum, and kind of argued about which of those is the best one to use. But all they give you is a sort of binary response of can a species live here or can it not, or will it grow here or will it won't. And this method of kind of referring all of those temperatures back off the curve into your matrix of numbers, and then using these matrices as your analyzable data frames, I think is a really nice method of getting to that. And if we can use that for functional rates rather than for organismal thermal performance curves, we could start to generate landscape scale maps of like entire ecological functional processes. So I'm going to start doing that for resource removal by ants. So we've got a data set of ant foraging rates at about 230 locations across the SAFE project, which I'm going to use the microclimate data for, and try and kind of create a curve like this for the function of the entire ant community, and then refer it back to this. But I think SAFE, because of the gradient of land use change and because of all the data sets we have, it could easily be done for things like decomposition, herbivory, and some other kind of key functions. And most of the data's there already for that. And there could be just some quite simple field experiments that would enable us to generate these things, which I think is a more enlightening future prospect for microclimate research than looking at organismal physiology. So that's that. If you've got any questions, then please ask. Thank you very much.